moving coil galvanometer, moving coil galvanometer, moving coil galvanometer. What is the moving coil galvanometer? Actually, what is the galvanometer? Galvanometer is a device. Galvanometer is a device. Galvanometer is a device used. Galvanometer is a device used to detect currents. Used to detect currents. Used to detect currents. Also, it is used to measure currents. Used to detect current, to measure currents, detect currents, measure currents, measure currents. Also, we can measure potential differences. With the help of galvanometer, we can detect current, we can measure current. Also, we can convert galvanometer to voltmeter and we can measure potential differences. Also, we can measure potential differences. Measure potential differences. Understood?
Yes, sir.
Now, moving coil galvanometer device used to detect current, sir, whether current is flowing or not. If current flows through the circuit, then galvanometer needle will deflect. If no current, then needle will be at the middle of the scale. Okay,
Yes.
we use this galvanometer in the experiment, meter bridge experiment. In the
Yes,
meter
sir.
bridge experiment, to find unknown resistance, we use in the meter bridge galvanometer. Galvanometer, if current flows, then galvanometer needle will deflect either right or left side from the middle of the scale. If no current flows through galvanometer, then needle will not deflect. Needle will be at the middle of the scale. Now, moving coil galvanometer. Now, this galvanometer, on what principle? What is the principle of galvanometer? Principle of galvanometer. Principle of galvanometer. In the examination, they ask a question. What principle galvanometer works? Principle of working of galvanometer. Principle of working of galvanometer. Principle of working of galvanometer. Galvanometer works on the principle that a current carrying coil placed in uniform magnetic field experiences a torque. A current carrying coil placed in current carrying coil placed in uniform magnetic field, placed in uniform magnetic field, placed in uniform magnetic field experiences a torque. Experiences torque. Understood what is the concept here? A current carrying coil placed in uniform magnetic field experiences a torque. This is the principle. And then when current passes through coil and the coil is in uniform magnetic field, it experiences a torque. Torque means the coil will rotate. As the coil rotates, the amount of rotation depends on the strength of current. So we can measure current by seeing the amount of deflection of the coil. So principle, then construction of moving coil galvanometer. Construction of moving coil galvanometer. Construction of moving coil galvanometer, MCG, moving coil galvanometer. It consists of galvanometer, moving coil galvanometer consists of a coil. It consists of a coil. The coil is made with a thin copper wire, and that wire is wound on a soft iron, cylindrical soft iron piece. So in the construction, you have to write galvanometer consists of moving coil galvanometer. Moving coil galvanometer consists of a coil. Consists of a coil made with a thin copper wire. Made with a thin copper wire. Thin copper wire. Thin copper wire. Coil made with a thin copper wire. The copper wire is wound on. The copper wire is wound on. Wound on where? The copper wire is wound on wound on where? It is wound on a cylindrical soft iron piece. Cylindrical soft iron piece. Why it is wound on cylindrical soft iron piece? Because soft iron has a high permeability. Soft iron is a ferromagnetic material. Ferromagnetic material has high permeability. So we can increase the strength. We can concentrate the magnetic field in that area. In another way, we can say that the soft iron piece is used so that the strength of magnetic field can be increased. Also, due to this cylindrical soft iron piece, we will get a radial magnetic field. What is radial magnetic field? We will do now. Moving coil galvanometer consists of a coil made with a thin copper wire. The copper wire is wound on a cylindrical soft iron piece. And also, this coil is arranged. This coil is placed between two cylindrical shaped magnetic poles. This coil is placed between two poles of a magnet. Two cylindrical shaped poles. Two concave shaped poles of a magnet. Two concave shaped poles of a magnet. And the coil is placed between north pole and south pole of a magnet, and the pole pieces, the poles are in a concave shape. The poles of this magnet are in concave shape. Why concave shape? Why concave shape means because to provide radial magnetic field. Okay, what is the use of radial magnetic field? What is the use means so that The deflection of the coil. When current passes through the coil, coil will deflect. The deflection is proportional to strength of current. That will do now a mathematical treatment in that you will understand. The coil is placed, and also the coil is free to rotate. The coil is arranged in such a way that the coil is free to rotate. The coil is not fixed. The coil is free to rotate between the poles of magnet. The coil is free to rotate between the poles of magnet, Okay, and also the coil is connected to one spring. The coil is connected to one spring, and like this, you see. For example, suppose we have a cylindrical soft iron piece. Suppose this is a cylindrical soft iron piece. Cylindrical soft iron piece. This is cylindrical soft iron piece. On that cylindrical soft iron piece, we we wind the wire. The wire is wound on this cylindrical soft iron. Suppose this is a wire. This wire is made on this line. This is one turning, and they put several turnings on this soft iron piece, like several turnings. Yes, like this is. And if you see from the top, the view will be like this. Suppose from the top, the cylindrical shaped, the cross section of this piece appears in a circle like this. If you see from the top, and if you see from the top, the shape, the cylindrical piece, it appears, a cross section appears in a circular shape. And also the windings on this appear in the form like this. This is one turning, this is another turning, and another turning, like it appears like the coil appears like these are turnings of the coil. And this is a soft iron piece, soft iron piece, soft iron piece. I hope you're following.
Yes, sir.
I'll erase here and I do again. Here, it consists of placed between two concave shaped magnetic poles. Two concave shaped magnetic. The coil is placed between two concave shaped poles of magnet. The coil is free to rotate, and also the coil is wound on. The coil is wound on a cylindrical soft iron piece. For example, this is a cylindrical piece. I draw diagram again. Cylindrical piece. On this wire is wound. This is one turning, next turning, like this. Several times they turn wound on this soft iron piece. Okay, and if you see this, if you see from the top, this is a cylindrical piece. This is a cylindrical piece, and on this coil is wound. The coil is made on this like this. Understood? This is one turning. This is another turning. This is another turning. Another turning like this. Several times they rotate like this. And if you see from the top, this is a coil. The coil appears like this. This is a cylindrical shape and a circular shape. On the top cross section of the cylindrical piece is circle, and here is the windings are given like this. These are the windings. One winding, second, third. Yes. Okay. Now this is the coil. This is your coil, and this is the cylindrical soft iron piece. This is a cylindrical soft iron piece. Cylindrical soft iron piece. Cylindrical soft iron piece. Okay. Are you following? Are you following this one? Now,
Yes, sir.
this cylindrical soft iron piece is placed between two concave shaped poles. There are two concave shaped poles. This is one. This is one. This is one pole, not pole of this one. This is one pole, and there is another pole here. South pole, north pole, and south pole. The two poles of a magnet. These poles pieces are in concave shaped, and here we keep this coil is placed between here. The coil is placed between these two poles. The coil is placed between these two poles. And the coil. This is the coil, and this is the coil. Yes. Now the magnetic field lines, from north to south, they go from north to south. And here, what is the advantage of this? Even if the coil is rotated from that position, for any position of the coil, the magnetic field lines are parallel to plane of the coil. Magnetic field lines are parallel to plane of the coil. Magnetic lines parallel to plane means the perpendicular drawn to plane of the coil makes 90 degrees. So even if the coil rotates, these are magnetic lines like this. These are the magnetic lines. Magnetic lines always parallel to plane of the coil. Even if the coil rotates to some other position, for example, the coil is rotated to some other position. For example, to some other position like this is. Suppose the coil is rotated to this place. Suppose this is north pole and this is the south pole. Yes, this is south pole. Even if the coil is rotated to some other place, even if the coil is rotated to some other place like this, coil is rotated like this, even if the coil is rotated to some other place. In this case also magnetic lines are parallel to this plane of the, this is the magnetic field now. So magnetic field is always parallel to plane of the coil. Magnetic field parallel to plane means a normal drawn to plane of the coil makes 90 degrees with B bar. So in the torque formula tau is equal to NIAB sin alpha always 90 degrees. Is it okay? Now you see moving coil galvanometer consists of a coil. The coil is made with a copper wire and the wire is wound on a cylindrical soft iron piece. The coil is placed between two concave shaped poles of a magnet and also the coil is free to rotate between the two poles of the magnet. And one more point, a spring is connected to the coil, children. A spring is connected to the coil. A spring is connected to the coil. I show that spring. A spring is connected to the coil. Spring. Yes. A spring is connected to the coil. What is the use of the spring? This is a spring. A spring is connected to the coil. The spring will bring back the coil to normal position. For example, if a coil rotates, if coil rotates along with the coil, spring also will be twisted. Because as the spring is connected to the coil, as the spring is connected to the coil, when coil is rotated, the spring also will rotate. Spring rotate means spring will be twisted. When spring is twisted, spring will give a counter torque. Counter torque in the sense it opposes the torque given by the current. So the coil will rotate. As the coil rotate more and more angle, spring also twisted more and more. So after some angle of rotation, the torque in the spring is equal to torque due to current. So there the coil will come to equilibrium position. So now this is the diagram. Understood? And also one pointer is connected to the coil. One pointer is connected to the coil. One pointer is connected to the coil. This pointer will move on a graduated scale. The pointer will move when coil is rotated. As the pointer is connected to the coil, the pointer will move on a scale, graduated scale. Graduated scale means they put readings on the scale, 0 ampere, 10 microampere, 20 microampere, like this. This is a graduated scale. Yes, this is the scale. Graduated scale. Graduated scale means markings are given on the scale by passing known currents through the coil. By passing known currents through the coil, we first graduate the scale. Graduated scale. So this is the diagram of moving coil galvanometer. Diagram of moving coil galvanometer. The other side is, other one is a spring here. This is a spring here. And this is the coil. This is a coil. This is a coil. Under the copper wire. And this is a spring. This is a spring. This is spring. Okay. The coil is connected to a spring. The coil is connected. The coil is connected. The coil is connected to a spring. What is the use of spring? The spring will give a counter torque. The coil is connected to a spring. The spring gives a counter torque. The spring gives a counter torque to the torque given by the current. Counter torque to the torque on the coil, to the torque on the coil given by current. And when current passes through coil, torque is reduced. Due to the torque, coil will rotate. As the coil rotates, the spring gives a counter torque. Counter torque means the spring will be twisted. So as the spring is twisted, it gives a counter torque. And also a pointer is connected to the pointer is connected to, yes, connected to what? A pointer is connected to the coil. A pointer is connected to the coil. And this pointer moves on. This pointer moves on a graduated scale. When coil is rotated, the pointer moves on a graduated scale. This pointer moves on a graduated scale. Moves on a graduated scale. This is about construction. Understood, I think? This is about the construction of moving coil galvanometer. Now, working of moving coil galvanometer. Working means we explain how we are able to find the current. Working, what is working? The current that you have to measure is passed through the coil. When current is passed through the coil, what acts on the coil? When current is passed through the coil. Yes, when current is passed through the coil, torque acts on the coil. Torque acts on the coil. Torque acts on the coil. Okay, due to the torque, the coil will rotate. Therefore, the coil will rotate. Therefore, the coil will rotate. The coil will rotate. How long the coil will rotate? The coil will rotate until the coil will rotate. The coil will rotate until the coil will rotate until The coil will rotate until the torque due to current and the torque due to spring are equal. The coil will rotate until the torque due to current is equal to counter torque given by the spring is equal to counter torque given by the spring is equal to counter torque given by the spring. Also here let k is equal to, you see, suppose the coil is rotated by theta angle. Let theta is the angle of rotation of the coil. Let theta is equal to angle of rotation of the coil. Angle of rotation of the coil. Let theta is equal to angle through which coil is rotated. Angle of rotation of coil. Angle of rotation of the coil. To current equal to torque given by the spring. On to plane of the coil and magnetic field. NIAB sin alpha equal k into theta. Here alpha is 90 degrees. Here alpha is 90 degrees due to radial magnetic field. Here alpha is equal to 90 degrees. 90 degrees due to radial field. Radial magnetic field. The radial magnetic field is due to concave shaped poles. Alpha is 90 degrees due to radial magnetic field. Therefore, if alpha 90 degrees, sin alpha is 1. Therefore, NIAB is equal to k theta. From this you will get I is equal to k by NAB into theta. NAB, where theta is the angle of deflection of the coil. When coil is rotated, the pointer will move on the scale. And pointer will show some reading. So the reading shown on the scale, that depends upon angle of deflection. And again, angle of deflection theta depends on current. And k by NAB, it is a constant. K constant, N constant, A area of coil, strength of field, all constant. Therefore, from this you can say I proportional to theta. So more the deflection, more the current. So by using the graduated scale, by measuring angle of deflection, you can measure what is theta. As I proportional to theta. Therefore, by measuring angle of deflection, of the coil, by measuring angle of deflection, we can measure current. And we are getting a linear variation between current and deflection. There is a linear variation. More the current, more the deflection. So from the angle of deflection means angle of deflection is nothing but the deflection shown on the graduated scale by the pointer. So by seeing angle of deflection, by seeing the reading of the pointer on the scale, we can say what is the current. I proportional to theta. By measuring angle of deflection, we can measure current. So this is about moving coil galvanometer. Hello. This is
Yes.
okay. You see now today what we did here. Today we did about moving coil galvanometer. Device used to detect currents, also to measure potential differences. Its principle is current carrying coil placed in uniform magnetic field experiences a torque. And by measuring torque, we say what is the current. Construction में a moving coil galvanometer consists of a coil made with a thin copper wire. The copper wire is wound on a cylindrical soft iron piece. Why cylindrical soft iron piece? Because, and this is also a short answer question, what is the need of cylindrical soft iron piece? Soft iron piece helps to make magnetic field strong. Also, it helps in providing radial magnetic field. What do you mean by radial magnetic field? The field lines are along the radius of the concave shaped poles. As the field lines are along the radius of concave shaped poles, the direction of magnetic field is always parallel to plane of the coil. Always parallel to plane of the coil means magnetic field is perpendicular to normal drawn to plane of the coil. As magnetic field is perpendicular to magnetic field is perpendicular to plane. Magnetic field is parallel to plane. Parallel to plane means with normal drawn to plane of the coil makes 90 degrees. So in the formula torque NIAB sin alpha is 90 degrees. Even if the coil rotates, even for any position of the coil, alpha always 90 degrees. From there you are getting NIAB is equal to k theta. From that you are getting I is equal to k by NAB theta. That means you are getting I proportional to theta. So by measuring theta, you can measure what is current.
Yes.
Okay, right.